Good day, students. Today, our topic of discussion is the reduction of reflectivity of lens surfaces. Well, this is an application of thin film interference. And here, when light falls on any glass surface, a fraction of it gets reflected and a fraction of it gets transmitted. Now, the fraction that is reflected can be calculated using the reflection coefficient, and we see that it has a significant amount of reflection. Thus, to overcome this, what can we do? What can be used to reduce the reflection from lens surfaces? Well, as the picture shown, you can see a lot of camera lenses are here, and all of these camera lenses have AR coatings, that is anti-reflective coatings. Now, the idea of anti-reflective coatings emerged from thin film interference. Now, here in the picture shown, we can see a glass plate on which the reflection of the flashlight of the camera taking the picture is seen. Okay, so this reflection is actually unnecessary. It is not needed here. So how do we reduce this reflection factor? Now for that, the reflection coefficient was given as capital R is equal to N1 minus N2 divided by N1 plus N2 the whole square, where N2 is the refractive index of the component placed in a surrounding medium of refractive index N1. Usually, if we take glass in our hand, the surrounding medium is air and N2 is the refractive index of glass. Now, there are different types of glass. Now, let us take a comparison here. For crown glass in air, the reflection coefficient is given as N1 is 1 and N2 is the refractive index of crown glass 1.5. Thus, capital R is calculated to be, you can do the calculations, you will get 0.04, that is 4%. Hence, 4% light is reflected from each crown glass surface. For flint glass in air, flint glass is a slightly more denser material. The reflection coefficient is calculated to be 0.06. Here the difference is the refractive index of flint glass is 1.67. This means that 6% of light is reflected from each flint glass surface. So in many of the optical instruments, we don't have a single lens surface. We have multiple lens surfaces. And if we have such fractions of light reflected from each of the lens surface, then only a small fraction will get into the optical instrument and reach the detector or the sensor. There comes the usage of anti-reflective coatings. Thus, in optical instruments where we have a large number of lens surfaces, there will be a significant loss in intensity by reflection from each surface. So, to reduce the reflection loss, lens surfaces are coated with a thin, transparent, non-reflecting film whose refractive index is less than that of the lens material. And this technique of reducing the reflection loss is called blooming. So here on the right side, we can see that there are 3 layers of refractive indices. N is equal to 1 is that of air, and N is equal to 1.5 is that of crown glass. So upon this lens of refractive index 1.5, if we have a coating of refractive index 1.3 and sufficient thickness lambda by 4n, we can have or we can reduce the reflection loss from the lens surface. The refractive index of this thin transparent non-reflecting film is given by square root of the products of refractive indices of glass and air. That is, n of film is given by square root of n of glass into n of air. And the thickness of the film has to be lambda by 4n. Here lambda is the wavelength of the light that we want to detect. Okay, the wavelength of light that we would like to detect is selected as lambda, and lambda by 4n should be the thickness of the film. Now in the figure you can see that when light is incident upon this coating, light gets reflected from the upper surface and from the upper surface of the lens, and these two rays happen to interfere. Now the path difference, geometrical path difference between these two rays is twice of the distance of the thickness of the thin film, that is twice of lambda by 4n. Now, is there any phase change upon reflection? On both the cases, from the top of the thin film, light is passing from a rarer medium air to a denser medium, that of film. So, phase change does not take place. Again, on top of the lens surface, light is entering from a rarer medium of the film to a denser medium, that of the lens. Again, here on reflection, there will be no phase change. Thus, there will be no path difference due to phase change. So, path difference will be twice of lambda by 4n. Path difference of the interfering waves is lambda by 2n. That is twice lambda by 4n gives lambda by 2n. Now, this condition, that is, the path difference being an odd integral multiple of half wavelength, this is satisfied for destructive interference. Okay, this is the general condition for destructive interference, and hence for this particular lambda we have destructive interference and no reflection takes place. The wavelengths that we usually select is the wavelength that is most sensitive for our eyes. For human eyes, the wavelengths that are most sensitive is green and yellow. Okay, so in these ranges of wavelengths, we need the light to pass completely and reach the detector. So here, the reflection loss can be reduced for particular wavelengths of green and yellow, but the remaining wavelengths, they may suffer or they may have reflection losses. So that is why even though anti-reflective coatings are coated on the camera surface, they are only for the wavelengths of green and yellow, and the remaining wavelengths of blue and red, they suffer reflection losses, and hence the camera lenses appear or they have a purple hue. Here are a few examples showing the significance of anti-reflective coatings on lenses. See, on the left side of the figure, we see a man with wearing glasses which do not have AR coatings. But the same person, when he used glasses of AR coatings, we can clearly see his eyes. Okay, so his face can be clearly seen or his eyes can be clearly seen. This is one of the advantages of AR coated lenses. Now here we have a series of pictures that show the difference with anti-reflective coating and without anti-reflective coating. See, in all these figures we can see that the image has become more clearer. Okay, the clarity has increased, the glare has reduced. This is because we have reduced the reflection losses. Thus, AR coatings or anti-reflective coatings has become an important discovery related to imaging, and this has emerged as an application of thin film interference. That's all for today. Thank you, dear students.